Hello, everyone. I'm talking about our paper titled ETH-tight algorithms for geometric intersection graphs, now in polynomial space. So this is a joint work with Fedor Fomin, Petr Golovac, and Saket Saurabh, and I'm Tan. So let me start by talking about our results. So we consider different graph problems in the intersection graphs of similarly sized fat objects in D dimensions. And we get sub-exponential time algorithms using polynomial space. So if you look at D equal to 2, then this is like 2 to the order square root n. And we get these kinds of algorithms for different graph problems like independent set, vertex cover, dominating set, and different kinds of connectivity problems, as well as cycle and path problems. So we work in this framework of Deberg et al. So they actually initiated this study, and they gave sub-exponential time algorithms for all of these problems in the intersection graphs of similarly sized fat objects. And they also showed that this running time is tight, assuming the exponential time hypothesis. But one drawback of this paper is that the space requirement of their algorithm is also sub-exponential. So a natural question is, can you get the same running time, but can you improve the space to polynomial? And we know that the running time cannot be improved because of this lower bound, but maybe we can improve space. So let me first talk about this notion of similarly sized fat objects. So here I have three objects denoted in blue. So this is just an equilateral triangle. And then I have also drawn like an in circle and an out circle for each of these objects. Okay. So if you look at this equilateral triangle, then the in circle and out circle, they don't differ by too much in terms of their size. And the same is true for this object as well. So the ratio of radius of in circle and out circle, it's not too large. But here, if you look at this triangle, it's like very long and skinny. So the in circle is very, very tiny, but then the out circle is very large. And so this does not qualify as a fat object. So that is fat objects. And similarly sized just means that if you look at any two objects in the collection, let's say this one and this one, then, and if you look at the diameter of every object, then the ratio of diameter, like the ratio of maximum diameter to the minimum diameter in your collection, that's also upper bounded by constant. So that's the notion of similarly sizedness. So we look at these similarly sized fat objects. So, and we have the intersection graph of these objects. So given this graph G, this intersection graph, we construct this auxiliary graph GP. So the way we construct it is we construct this partition P using the geometry of the graph. And this is a partition of the original vertex set, such that each VI is a union of at most k cliques. So here in this example, if you look at this graph G, this partition, the vertices are partitioned into three parts, V1, V2, and V3. And each VI is a union of at most 3 cliques here. In fact, like V2 is just one. And then if you look at the graph induced by this partition, then you get GP. So here we have an edge between V1 and V2 because there are two vertices, one in V1 and one in V2, such that there is an edge between them. And you can show that if you have the intersection graph of similarly sized fat objects, then the maximum degree of GP is also constant. So these two properties follow from the fact that we are dealing with similarly sized fat objects. Okay, so the key lemma or key result from this Deberg et al. Paper is that they construct this clique-based balance separator for the intersection graph using this graph GP. So the way they construct it is they show that there exists a set S containing some of these super vertices V1, V2. So note that each VI is a subset of original vertices. So here I'm showing them using these circles. And each of them is a union of at most k cliques. And if you look at X, which is the union of all the VIs in the separator, so that is a separator for the original graph. And what this means is that if you delete X, then your graph breaks down into two parts, A and B, each containing at most 2n over 3 vertices, let's say. And there is no edge going from A to B. And they also show that the weight of this separator is sublinear. And the way they define this weight is they add basically the log of Vi over all the VIs in the separator. And the exact value or exact upper bound on this weight of separator is n to the power 1 minus 1 over d. So again, if d is 2, then we have like square root n weight separator. So this separator, they show that it exists. And if you are given the geometric representation of these objects, then you can also compute it pretty effectively. But then if the input is only the intersection graph without the geometry, then it's not clear how to compute this separator. So what they observe is that the existence of sublinear weight separator implies that the weighted tree width of this graph GP is sublinear. So I'm not going to define what weighted tree width or even tree width is, but this implication is fairly straightforward. And then they use a constant approximation to the weighted tree width, which you can compute in single exponential time in tree width. And remember, the tree width bound is also sublinear, so you get a sub-exponential time algorithm to compute this constant approximation. And once you have this, they do dynamic programming over this approximate tree width decomposition. And here you have to kind of adapt the classic algorithms that use tree width in this clique-based separator approach. And here they use the properties of GP, namely that each VI is union of at most k cliques and the degree is constant. Okay. So since we want to improve the space requirement to polynomial, tree depth is a natural parameter. So the main idea is that we use tree depth instead of tree width to get the same running time, but polynomial space. So let me talk about this parameter tree depth. So here I have an example. So on the left, we have some graph G, and on the right, we have a tree depth decomposition. So a tree depth decomposition is just a pair F and a bijection phi. So this is a bijection between V of G and V of F. And F is a forest. In fact, in this example, it's just, and the property that this bijection should satisfy is that if you have an edge in the original graph, then the corresponding two vertices must have an ancestor-descendant relation. So here we have an edge between this green vertex and this blue vertex, then they have this ancestor-descendant relation in F. Again, there is an edge between this blue vertex and this purple vertex, so there is an ancestor-descendant relation. And given this, then the depth of this decomposition is just the maximum length of a root to leaf path. So here the length will be 1, 2, 3, 4. And so the depth of this will be 4. And then the tree depth of your graph is just the minimum depth over all possible tree depth decompositions of your graph. So this is the definition of tree depth. So tree depth is a very well studied parameter. And the good news is that there are single exponential algorithms in terms of tree depth. They are recursive algorithms, and they only require polynomial space for many graph problems. There is also somewhat good news is that tree depth is bounded in terms of tree width. So in general, it can be larger than tree width, but not too large. It is within log n factor. But if you use this relation naively, then you will get you will incur a log n factor in the exponent. And this means that just using this relation will not give you an optimal running. Remember that the ETH lower bound was only 2 to the omega n to the 1 minus 1 over d. So this log n factor is what we want to avoid. And this is this requires more work. So we want to bound the weighted tree depth of our graph. Remember that Deberg et al. Were bounding the weighted tree width. So the first 3 steps will be similar to the Deberg et al. Approach. So remember that there exists a sublinear weight separator for the graph. And this implies that the weighted tree width is bounded, which means that even a constant approximation to weighted tree width is bounded. So these 3 steps are exactly same as Deberg et al. Paper. Now, once you compute this constant approximation to weighted tree width, we observe that using the properties of tree decomposition, there exists a separator bag of sublinear weight, which is like a balance separator. And since we are dealing with a constant approximation to this weighted tree width, this separator bag kind of works as a constant approximation to this sublinear weight separator, which was only we only knew that it exists, but we didn't know how to compute it. So here we can compute a constant approximation to it. And once you have it, you add it to your tree depth decomposition as a root, and then you just recurse, because once you delete the vertices in this separator, the graph contains like each connected component contains at most 2n/3 vertices, and so you can recurse. So again, we have the same picture. So now let us assume that this S is a constant approximation to the separator. So once you delete these vertices in the separator, we can group the remaining vertices into A and B such that the maximum size of A and B is at most 2n/3. And again, we can use the same relation, like since the graph induced on A contains at most 2n/3 vertices, there exists a sublinear weight separator. But then the advantage is that we have an additional factor of 2n/3. And so the weight of this separator will be 2n/3 the whole to the power 1 minus 1. And same for B. And if you kind of keep recursing like this, then after I levels, the number of vertices in the graph are at most 2/3 to the power I minus 1 times n. And so the weight you get is the whole to the power 1 minus 1 verti. And so what we observe is that if you compute these separators recursively, then the weights kind of fall geometrically. And so if you look at the maximum weight of separators along root to leaf path, then it is kind of a geometric series. And then the weight is kind of dominated by the largest term, which is n to the power 1 minus 1. So this is how we bound the weighted tree. Okay. So this is our theorem that you can compute a weighted tree depth decomposition for the intersection graphs of similarly sized fat objects. The weighted depth is n to the power 1 minus 1/d, just like the bound for weighted tree width. The time it takes to compute this decomposition is sub-exponential, and it's mainly dominated by the time to compute approximate tree width, tree decomposition every time. So the time is sub-exponential, and we observe that these constant approximation to tree width, they only require polynomial space. And so we can also compute this tree depth decomposition in polynomial space. And this is good because like we want to use this tree depth decomposition to get polynomial space algorithms for the graph problems. So it won't be good if like this step itself requires exponential space. So this is our result. And now I'll talk about how to use this tree depth decomposition. So suppose you have a graph problem, and this graph problem has the property that if you have any optimal solution T, then it has bounded intersection with any clique in your graph. So if you look at T intersection C, where C is a clique, then the size of this intersection is bounded by some alpha, which is constant. Or maybe you have this property for the complement of this optimal solution, even that is fine. So how is this useful? Remember that each Vi in this partition P is a union of at most k cliques. And what this means is that the intersection of Vi with an optimal solution or its complement, that is upper bounded by alpha times k. And alpha is a constant, k is a constant. So even this intersection is upper bounded by a constant. So consider this level 1 separator S, which is like, let's say V1, V2, and so on. And remember that it has a sublinear weight. So what we are going to do is to try all possible intersections of the optimal solution with every Vi in the separator. And we know that the size of every intersection is at most alpha k. So we'll just enumerate all possible subsets of size at most alpha. So how many possibilities are there for a fixed Vi? It's like sum of Vi choose j going from 0 to alpha k. And this you can upper bound by this quantity, 1 plus Vi to the power alpha k. And remember that alpha k is a constant, so so the exponent is constant, and we are going to try all possibilities for every vi, and so we take a product. So we have this term, and you can rewrite this term as like x of sum of logs. So then we get this expression, and this expression will suddenly look familiar. And this is because we defined the weight of this separator in exactly the same. So this is exactly how the weight of S was defined. And so we get that the number of possibilities is basically 2 to the power order weight of separator. And since we had this bound on the weight of separator, we get that the number of possibilities we are going to try is sub-exponential. And so for every possibility, we'll basically make a recursive call. And remember that the separator weights kind of fall geometrically at every level. And so we can show that this sort of recursion will lead to sub-exponential running time. And if you kind of do this recursive algorithm, implement it carefully, then it will also only require polynomial space. Okay. So now I'll talk about how the graph problems we consider, they satisfy this bounded clique intersection property. So for some problems, this is very trivial to see. For example, if you have independent set, then trivially it can select at most one vertex from a clique. Otherwise, if you have two vertices from a clique, then they will have an edge. And if you have vertex cover, then it's complement of independent set. So it can leave out at most one vertex. And remember that this is also fine. And even if you add the restriction that your vertex cover must induce a connected subgraph of the original graph, but that's still a vertex cover, so the same property. If you have dominating set, then there is a lemma in Debug et al. Paper which shows that it can choose at most k square times delta vertices from it. And remember that both k and delta are constant, so this is still a constant. But for maximum weight independent set, you just use this property and basically use a simple recursive algorithms. Whereas for dominating set, you need to use some additional ideas because a simple recursion does not suffice. Then for Steiner tree, there is a similar lemma, which again gives a similar kind of bound, k square times delta, and again, this is a constant. For feedback vertex set, remember the goal is to remove some or delete some vertices so that after deleting those vertices, the graph is acyclic. And in odd cycle transversal, you want to delete vertices so that the remaining graph is bipartite. So in other words, it doesn't have any odd length cycles. So remember that if you leave at least 3 vertices in a tree, then that induces a triangle, which is not allowed in FVS or OCT. So any solution to FVS or OCT has to select at least C minus 2 vertices from every key. In other words, it can leave out at most 2. So even these two problems satisfy this bounded clique intersection property. So for these 4 problems, feedback vertex set, odd cycle transversal, Steiner tree, and connected vertex cover, we use this cut and count technique. So this was originally introduced for designing single exponential time algorithms for these sorts of problems, but single exponential in tree width. But recently, Hegerfeld and Kratz gave single exponential algorithms in terms of tree depth. And these cut and count algorithms are basically randomized algorithms, and they use this famous isolation lemma of Mulmule Vazirani Vazirani. So the approach of this cut and count technique is to basically reduce the problem of, let's say, finding an FBS of size at most k to counting cuts in the graph, which are kind of consistent with the feasible solution to the problem. So if you have an FBS of size at most k, then you are counting cuts that satisfy some property. Okay. And the way you count this in the algorithm of Hegerfeld and Kratz is by recursively computing some polynomials using your tree depth decomposition. And these polynomials will have coefficients which will encode the number of consistent cuts. So this is like an algebraic approach to this cut and count technique. And we kind of, in our approach, we have to prune the number of recursive calls using this bounded clique intersection property, which I just talked. And this is how we get sub-exponential time polynomial space algorithms. And because of this isolation lemma, our algorithms are also random. Now we also consider some cycle and path problems, for example, Hamiltonian path, Hamiltonian cycle, and cycle cover. So here we have an additional requirement that we actually need geometric representation. So all the previous algorithms, they worked without geometry, but here we need geometric representation. But if you have this geometric representation, then you can efficiently find an equivalent subgraph. But this has the strong property that even the unweighted tree depth is sublinear. And this is equivalent in the sense that if this subgraph has an Hamiltonian path, then also the original graph has Hamiltonian path, and so on. And then you can directly use a cut and count based algorithm of Nedelov et al., which is also single exponential in the tree depth. And this is how we get sub-exponential time polynomial space algorithms for these cycle and path problems. And again, these are randomized because it's a cut and count application. So to summarize, we design sub-exponential time algorithms for many graph problems in the intersection graphs of similarly sized fat objects, just like Deberg et al. And for this, we introduce the notion of weighted tree depth. But we improve the space to polynomial. So this is the main contribution here. And remember that there is an ETH lower bound which is tight. So the running time is tight, and we get polynomial space. So I'll leave you with a couple of open problems. So as I mentioned, these cut and count algorithms are inherently randomized because of this application of isolation lemma. And it is also known that in general, you cannot de-randomize isolation lemma. But maybe it's possible to get de-randomized or like deterministic algorithms for geometric intersection graphs. Maybe it's possible to de-randomize for this special case. So that's the first open problem. And the second problem is related to this connected dominating set. So Deberg et al. Paper also gives us a sub-exponential time and space algorithm for connected dominating set. And in fact, this paper of Hegerfeld and Kratz, they also give a single exponential time in tree depth algorithm for this problem using polynomial space. So it may seem that if you kind of combine these two results, like the way we did for other problems like Steiner tree and feedback vertex set and so on, you might be able to get a sub-exponential time polynomial space algorithm for connected dominating set. But because of some technical reasons, we cannot adapt this approach for this problem. And so I'll leave you with the second open problem, which is, can you get a sub-exponential time polynomial space algorithm for connected dominating set? So these are the two open problems. Thanks for listening.